Hey there. So here we go with module 2 in our review for exam 1. So inorganic chemistry. Let's hit it. Let's get going. So chemistry is, if we get my PowerPoint going, the study of matter. And matter is anything that occupies space and has mass. Mass is the amount of matter an object has. Usually we measure this in grams. Elements are the simplest type of matter with unique chemical properties. And again, it's just a quick overview. Make sure you go back through your notes, make sure you go back through the material and get the details. The review guide will really help. An atom, so back to an atom is the simplest particle of an element that maintains the chemical properties. So like silver, gold, copper, or the ones we see a lot as we study life in the body would be carbon, oxygen, nitrogen, hydrogen. So isotopes occur when atoms of an element have a different number of neutrons. So if we look at the atomic number, this is the number of protons. This is like the fingerprint. This is what makes an atom, or a specific type of atom. So a hydrogen atom is identified by one proton. A calcium is identified by the number of protons. If we change the number of neutrons, we change the mass, and we call it an isotope. But it doesn't change what the atom actually is or what type of element it is. So then again, looking over here, we've got the name, the symbol, and the relative atomic mass. So if we look again closer at atoms, they consist of 3 subatomic particles. We've got protons, neutrons, and electrons. This is fundamental. If you haven't had chemistry, again, you're probably going to have spend more time with this, but it will certainly pay off. So protons are positive. I can remember this by looking at the T and thinking of a plus sign. They have a mass of about 1 AMU, and if you look at this, protons and neutrons have very similar mass number, and they're both found within the nucleus. Neutrons are neutral, so think neutral, neutron, and electrons have a negative charge, and I just visualize this E with the line right here and visualize it as a minus sign. And if we were to look for the electrons, they're going to be found in cloud, around the nucleus, rotating in orbitals or moving around. And if you look at their mass, it is almost nothing compared to the mass of protons and neutrons. So when we're looking at the mass of a molecule or an element, we're basically considering the mass of the protons and neutrons and not even bothering with the mass of the electrons. Okay, so here's the periodic table. You'll see this in the exam where you need, if you need it for information or if they're asking a question about it, do not feel like you have to memorize any parts of it. You just need to know how to use the information. So here, columns, like right here, 1, 2, are going to have similar chemical properties, and we'll go over this more. But these guys are all going to have 1 electron on their outer shell. These guys are all going to have 2, and they're going to want to readily get rid of those so that they can have a full outer shell. These guys over here are noble gases. We don't really talk about them. They're not really when we talk about organic chemistry, they're not so involved, but they have a full outer shell. But then if we hop over here to fluorine, fluorine's going to have 7 electrons in its outer shell. It's going to really want 8, so it's going to have a strong pull for 1 more electron. And again, we'll talk more about that. Rows, excuse me, are going to represent the number of energy levels for electrons. So if you remember, the first energy level has 1 orbital and can fit 2 electrons. So 1, 2, we add 1 more for helium. And then the next energy level can fit 8. And you can see how each element adds 1 more electron. And then the next energy level can fit 8 electrons. You can see how that adds, each one adds 1 electron to that outer orbital. So in our third energy level, we can fit 8 electrons. And if we have a full third energy level, we know we're probably at argon. So I think we've got all that. So This is an image that I use in Foundations of Science that I think is really helpful. I don't think our text really talked a lot about Lewis dot structures, but basically what they are symbols that show how many valence electrons there are. And I think this helps as you're working with chemistry and trying to figure out how an element will react, how it will bond. And these valence electrons are so crucial in determining how that element will bond or interact with other elements. So the big idea is that elements are going to gain or lose electrons in order to obtain a complete energy level. So like I said before, these guys are easily going to lose 1. These guys, it's going to be a lot easier for them to lose 2 than it would be for them to gain 6. So then if we go over here, we've got oxygen with 6, fluorine with 7. Fluorine, to get that full outer shell, is going to steal electrons, probably from one of these guys. And if you look over here, chlorine has 7 valence electrons. Same thing, it's just needing 1 more, and it's going to steal it typically from sodium, and then we get sodium chloride, our common table salt, and it forms a really natural bond. So we'll get more into this, but I hope this helps you get a little background and see how we're going to, these valence electrons are so important. So let's get into some of the bonding. First, we've got ionic bonding. Ionic bonds are formed when we have a metal and a non-metal that have lost or gained electrons and become cations or anions. So here, cations are positively charged. They are atoms or elements that have gained, sorry, got a little distraction, that have lost an electron. So sodium, for example, lost its electron, became positively charged, and becomes a cation. Chlorine, on the other hand, gained an electron, right, buddy, just say it, and became negatively charged. So now we've got positively charged sodium, and we've got negatively charged chlorine, and they're going to be attracted, and this is an ionic bond. All right, covalent bond, on the other hand, we don't have stealing, taking and losing, and then attraction based on charge like we did with ionic. With covalent, think of a company, think of sharing or working together to achieve that full outer shell or that full valence shell. So with hydrogen, it needs 2. If you look back at the periodic table here, hydrogen just has 1. In order to have that full outer shell, it's just that first shell. It needs 2 electrons. So to achieve that, it will often share with another hydrogen. And then the sharing gives them access. The hydrogens will orbit around both nuclei, and both hydrogens will have access to 2 electrons. They're both stable. They both have a full outer shell. Same thing with oxygen. So oxygen has 6 valence electrons. These 2 are lone pairs, or these guys are lone electrons, and they are going to form what we call a double bond, and those electrons will spend some of their time with this oxygen, some with this oxygen, and both oxygens are stable or happy, both have a complete outer shell. Same thing with chlorine. Here we've got a nice single bond. Nitrogen, with 5 electrons on its valence shell, will form 3 bonds. We call this a triple bond. Here are some examples of some common molecules we would deal with. Methane, and you see water here, where we get 1 hydrogen sharing 1 electron, and then oxygen sharing 1 electron, 1 hydrogen sharing 1 electron, oxygen sharing 1 electron, and now both are stable. And this is obviously a very common, very stable, very functional molecule, right? Water. So that leads us to hydrogen bonds. There are a couple of questions about hydrogen bonds on the exam. So you want to know kind of the properties. These are intermolecular forces. So just like the the internet is not like within one place, but I don't know how to explain this well, but I think you know what I'm talking about, I hope. This is between molecules. So these are the hydrogen bonds here between the water molecules. So because this hydrogen right here, it's fairly weak in terms of its ability to attract an electron compared to this oxygen. The oxygen is going to be like the big strong guy that the electrons are going to spend most of their time around. And so the oxygen ends up with a partial, I know you can't really see it very well, but a partial negative charge on this side. And the hydrogen ends up with a partial positive charge just because those electrons aren't spending as much time. And so the charge that you see here is more from the positively charged nucleus. So what we get is an attraction between water molecules. This is really cool because it helps water have this cool property called cohesion, where it stays together, and that really helps when we're talking about water moving through capillaries or water moving up trees. So we've got this nice cool sticking property, but it also has really important properties in the body. These are typically going to be weak bonds. Again, just kind of review the properties of hydrogen bonding. All right, a quick bonding summary. I have to pause. Okay, I'm back. So bonding. We've got 4 different types of bonds that you're going to want to be familiar with, and polar covalent, non-polar covalent kind of go together, but they're a little bit different. So polarity just has to do with is there an equal charge? So like with this chlorine and chlorine, think of it as a tug of war or an arm wrestling match. If you've got 2 equally matched partners, your match could go on for a long time as they tug for those electrons. And the electrons are going to spend about an equal amount of time with each because they're equally as strong or equally as electronegative or have similar attraction for those electrons. So this is nonpolar, meaning that pretty much everywhere the charge is going to be about the same. Here, if we have, say, a strong chlorine atom and a weaker hydrogen atom, those electrons are going to spend more time over here around the chlorine. And this is going to create what we talked about before with the water, a partial positive charge over here because we've got the proton and the hydrogen, and then a partial negative charge over here as all those electrons are spending time over here. So polar covalent, and this is kind of cool because now these can create attraction for other molecules, like we talked about with water. And then ionic, we have a complete transfer of one of the valence electrons. So sodium loses a valence electron, goes to chlorine. Chlorine now has a full valence shell. Sodium has a full valence shell, and opposites attract. They spend time together, and that's our ionic bond. And then hydrogen bonding, sorry, this one's kind of hard to see, but I know we've talked about this before. It's not a bond between 2 hydrogens, but it's a bond between polar parts of molecules. So in this case, in the most common case that we're going to deal with is water. All right. Okay, so let's kind of review and do a little bit of application with this. If the atomic number for sodium is 11 and the mass number is 24, this is a little bit different. And notice that the mass here, this number represents the mass. It's not necessarily going to be an even number because it's an average of the naturally occurring isotopes. So remember, the isotopes are going to have different number of neutrons. This, the atomic number, is our number of protons. So if the mass number is 24, how many protons, neutrons, and electrons are there? So the mass, the 24, comes from the total number of protons plus neutrons. Remember, the electrons, their weight is so small, it doesn't even factor in. So what we do is we take the mass number and we subtract the number of protons, and that'll give us the number of neutrons. We can kind of figure out everything else. So if we take 24 minus 11, that equals 13 neutrons. And then if sodium's neutral, it's going to have the same number of electrons as protons. But we also know that sodium's in that first column, so it's going to easily lose one and become a cation. But we're not going to deal with that when we're looking at this. So to take this further, how many grams are in 1 mole of sodium? Fairly straightforward question. Just look at the molar mass, because this is the mass of 1 mole of sodium. So if we took 6.02 times 10 to the 23rd molecules of sodium, this is the mass that it would have, which makes it pretty cool in calculating chemistry stuff. So then our next question, how many electrons are on sodium's outer shell? Well, we've got 1 electron that will easily be lost. And then what kind of bond will sodium likely form? These are the types of questions that you're going to see on the exam. And these are the concepts that you want to make sure you really understand so you can answer a variety of questions. So in this case, sodium's going to form a cation, and then it's going to be attracted to another anion. And for some reason, I have to click a bunch of times before I get my image. Come on. There it is. So here we see sodium with 2 electrons in the first shell, 8 electrons in the second shell, and then that third shell has just 1 little electron that is going to readily go away, get captured by something like chlorine, which then will become negatively charged, and then we end up with a sodium cation and a chlorine anion that form our ionic bond. All right, molarity. Moles can be a hard topic to wrap your brain around. I know this, it's hard to visualize. It's hard to understand what 6.02 times 10 to the 23rd even looks like or what it is. But again, like I said, take a little time, at least get familiar with the basics. And these topics are going to come up again. We really come back and hit molarity and osmolarity when we talk about membrane transport. It becomes really important when we look at IV solutions and stuff like that. Oh, it's okay. I want it. All right, so molarity, we're looking at the number of molecules present. So a question that you might see would be something like, what's the molecular mass of a molecule, which would be a combination of different number of atoms. So in this case, methane, which has 1 carbon and 4 hydrogens. So then we look at the periodic table and we look at the atomic mass of each of those. So carbon has an atomic mass of 12, hydrogen has an atomic mass of 1, and then we would say, okay, we've got 4 hydrogens, so we've got to multiply that by 4, and then the total mass of methane would be about 16 AMU, or atomic mass units. Now, if we have 2 moles of methane, basically we just double it, because that means we've got 2 of these. So that's how we figure out molar mass. Osmolarity is similar as osmoles per liter. So we're looking at the number of particles per liter. When we put a substance in water, a lot of substances will dissolve. Some substances will even dissociate or come apart. So in this case, if we look at salt, sodium chloride, it's going to dissolve, but it's also going to come apart and disassociate. Our sodium and our chlorine ions are going to come apart. On the other hand, sugar would dissolve, but it's not going to disassociate. It's going to stay a nice glucose molecule. So if we were to dissolve 3 moles of sodium chloride, what would the osmolarity be? So each mole of sodium chloride has 2 particles, sodium and chlorine. So we take 3 moles and we multiply it by 2 particles, and we get 6 osmolar. If we do the same thing with glucose, remember it doesn't disassociate, so what are we going to get for our osmolarity? We're going to get 3 moles times 1 mole particle per mole. and we get 3. Again, this will be really key when we talk about membrane transport in, I think, Module 5. So take time to really grasp this because we'll build on it. All right, we're getting close to wrapping this up. So water is super important because it has the ability to dissolve solutions or substances. 60% of our body is water. It can stabilize body temperature. It helps to protect. It serves as a place for chemical reactions to take place, and it also takes place in them, or participates in those. Serves as a mixing medium, and it's held together by hydrogen bonding. This is what creates cohesion, or that water sticking together. Again, super important. Ionic compounds are going to disassociate or separate. So our sodium chloride and our other electrolytes, covalent bonds like our carbohydrates are going to dissolve. Electrolytes, so when we dissolve something like sodium chloride, an ionic compound, we're going to get cations and anions that dissociate water. These are going to conduct electricity and carry a charge. Water has surface tension, adhesion, and cohesion, and resist large temperature changes, which you can imagine why that would be really important. All right, we're getting there. Acids and bases. So again, take time to review this topic, back through the material. This is just a quick overview. Acids are proton donors, bases are proton acceptors. The strength of the acid depends on its ability to disassociate in water, because as that acid comes into water and dissociate and has more hydrogen ions, that means more acidity, higher acidity. And remember, it's kind of opposite of what you would think. So go back through and look at, okay, as the pH increases, then I'm becoming more basic. As the pH decreases, becoming more acidic. Normal blood pH is about 7.35 to 4.5. Review what acidosis and alkalosis are, and keep in mind that it all depends on free hydrogen ions. All right, acids and bases lead us into buffers, and I think it's about where we're going to wrap up. So buffer systems are really important because remember that whole homeostasis thing. We have set point and we want to stay close to set point. Buffers are going to come into play in keeping us closer to set point. So say we have a large amount, an influx of acid. The buffer system is going to react with the hydrogen ions to create, let's see. So if we have an influx of acids, we get a flow this way, we create carbonic acid, and then the acidity doesn't, it kind of is, what's the right way to say it? Buffered out, like reduced as we reduce the number of free hydrogen ions. So we can monitor or adjust the acidity based on what's needed. So just a minute, okay, buddy. So what happens when we add an acid? If we add an acid, then the reaction shifts this way. We get more carbonic acid. If we add a base, it's going to shift this way. So you can kind of review that. And keep in mind, I love this quote by President Kimball I know Valentine's Day is next, but I love St. Patrick's Day. So I love this idea. Every time I say good luck to you, I always think of this. Remember also that if you succeed, it isn't because of luck. Success comes from faith and work and prayer and constant righteous effort. So good luck, you've got this. And I'll be posting the organic chemistry video shortly.